We are going to continue with our discussion regarding seepage and permeability through the soils, and our today's topic is flow nets. To give you a brief overview of what we have done so far, we have seen that the permeability through the soil can be determined by using these equations, and one of the most important things that we are entrusted to determine is the discharge or the total quantity of water that is flowing through the soil. And we have seen that in order to determine the discharge or the total quantity of water, there are two parameters which are important for us to determine. One is the hydraulic conductivity represented by K and the hydraulic gradient represented by I. In the previous few lectures, we have seen different methods for the determination of permeability coefficient K. Our today's discussion is based upon the determination of hydraulic gradient I. So we'll mainly cover one of the methods which is called flow nets. So we will see how by using flow nets we can determine the hydraulic gradient through any soil stratum. So what are flow nets? In order to understand the concept of flow nets, let's consider a pipe structure as we have seen in one of the previous lectures as well. So it is a U-shaped pipe, and in this pipe we have some soil filled at the center. Let's assume that this is sand which is being filled here. We are putting in water. There is water inflow from one end, and the water flows through this tube and it drains out from the other end. Now, it should be very obvious for you from this figure that the direction of flow of water would be something like this. So water will be flowing in this direction. Now, if I ask you that there is a particle of water which is somewhere over here as represented by the cursor, if I ask you that what will be the direction or of flow of that particle of water, or more precisely, if I ask you what will be the path adopted by the water particle, so you can probably tell me that this will be the path that will be adopted by different water particles. So these lines which are here, which I have represented here, and these lines which represent the flow path of water particles while moving from the soil, these lines are called as flow lines. So what are flow lines? Flow lines are the lines which represent the flow path of water particles through the soil. Now let's assume that this is our reference surface, which we call as datum. Now if this is the reference surface and I ask you that what will be the total head of this water level here, so you can probably tell me that this line represents the total head. In the same way, if I ask you that what is the total head at the other end, so you should be able to tell me based upon the knowledge that you have gained in previous lectures that the total head at this end will be represented by this line. Now, with this total head in the initial part and this total head at the final part, if I ask you to determine the total head anywhere in between these 2 points, that can be represented by a straight line like this. So this inclined line probably represents, this straight line definitely represents the total head. So this is how along this pipe length, the total head varies. So for example, from this point to this point, total head is constant at this level. And then once we start entering the soil, the head starts on decreasing. And this is very obvious from the knowledge that you have gained in the previous lectures that whenever water flows through soil, it loses some of its energy. And this loss of energy appears in the form of head loss. So the same phenomena is occurring here. As soon as the soil starts and the water flows through the soil, head starts decreasing, as can be represented by its decreasing trend. And when we reach this finish point of the soil, the head again becomes constant. And if I ask you that what is the head loss between the starting point and the ending point, the head loss can very easily be determined by simply by the difference of height between the two levels. Okay, so now we know the total head in the beginning, we know the total head in the end. Now, if I ask you, tell me what is the total head at the center of this soil specimen. So you can tell me that if this head, if this head loss is, let's say, H, then at the middle of the soil sample, the head would be somewhat like half of H. So if this total head loss is small h, at the middle of the soil sample, head loss would be half of it. The next question that I ask you, okay, at the middle of the sample, the head would be half of h or 0.5 h. Then across this pipe section, if I take three different points like this, point X, point Y, and point Z, and if I ask you that, okay, you're telling me that at the middle of the pipe, the head is half of h, but what is the head at point X? What is the head at point Y? And what is the head at point Z? Is the head at these 3 points going to be any different, or is it going to be the same across these 3 points? So, so from the principles of fluid mechanics, you can tell me that since it is pipe flow in which it is more like a pressure flow, so because of the pressure flow, the head anywhere within the pipe would be the same. So because of this reason, the head at point X, point Y, and point Z would be the same. And that same head would be the same as 0.5h. Now what I can do is, since the head at these 3 points is the same, I can draw a straight line connecting the points of same hydraulic head. This line, which represents the points with the same head, is known as an equipotential line. So what is an equipotential line? An equipotential line is a line which represents points which joins points with the same hydraulic head. So what we can do next is that we can try plotting other equipotential lines. So in the same way as we have drawn this line, we can draw further equipotential lines and other equipotential lines on the other end as well. So what these lines represent, each of these lines represent points with the same head. So anywhere if I move on this line, head is going to be the same. So these are called the equipotential lines. So what are flow nets? So flow net is a combination of flow lines and equipotential lines. So flow net, it basically comprises of two kinds of lines. One is the flow lines and second is the equipotential lines. So let's explore flow lines a little bit more. So you have seen that the flow lines are the lines which represent points which represents the flow path of water particles in the soil. And an important property of the flow lines is that the space between any two adjacent flow line, which is called as the flow path. For example, this is one flow path, there is the second flow path, there is the third flow path, and the fourth flow path. So the space between any two flow lines which is called as the flow path. The discharge through each flow path is the same. It means that the same amount of water is flowing through each flow path. In the same way, we can look at some of the important characteristics of equipotential lines. So we have seen that equipotential lines are the lines joining the points with equal head. So the space between two equipotential lines, like this space, and this space, they represent a drop in head. As we have seen in the previous slide, that each equipotential line, although each line is representing points with the same head, but the space between them, it represents a drop in head. So there is a head loss from moving from this equipotential line to the next equipotential line. There is certain head loss, which can also be seen by the downward slope of this line. Another important characteristic is that drop in head, this drop in head is the same between each equipotential line. So whatever was the head drop in this space, same would be the head drop in the second space and the third equipotential space, and so on. So it also means that if we put a piezometer on any place on a equipotential line, water will always rise to the same elevation. So if we install a piezometer here in this pipe, and even if we insert it more, the water level would always be the same, because at any point on a particular equipotential line, the water head would be the same. So let's see a slightly different case. Let's see a case in which we have a slightly different configuration compared to the previous one. Let's assume that we have the same tube, U-shaped tube, which has two different kinds of soil in it. One is sand, and there's another clay layer in the middle, and then again sand. Now, let's try to draw the flow nets through this one. Now, you know this, that since sand has a higher permeability than clay, so what we can do is we can write it like this, that K1, let's say K1 is the permeability coefficient of the sand layer, the same permeability coefficient of the sand layer, and let's call K2 as a coefficient of permeability of this clay layer. And since it is clay, so K2 is going to be less than K1. So how can we draw the flow lines first? So if we want to draw the flow net for this configuration, how can we draw the flow lines? So as it would be very clear that flow lines are the ones which represent the flow path of water particles. So how can we draw the flow paths of water? So yes, you might have guessed that the flow paths can be represented by straight lines like this. So a water while flowing through this soil would follow the straight lines as shown here. So these lines would represent the flow paths. So having drawn the flow lines, let's see how can we draw the equipotential lines. So before drawing the equipotential line, let's see how the head would vary across the soil profile. So you know from our discussion in the previous slide that the head in the beginning would be at this level. So while the water is flowing through the soil, the head would keep on decreasing something like this. So this would be the head loss or the decrease in head in the first soil. Now, what do you think? What will be the trend of this line going forward? Would this line follow the same path? Would the head loss become constant? Would the head loss increase? Would it decrease very sharply? Or would it go a little up? What would be the trend while the water is moving through this clay layer? Now, since the clay layer has high permeability, because since the clay layer has in fact low permeability, so because of the low permeability of the clay layer, water while moving through the clay layer would lose more energy. And because of high loss of energy or the high loss of head, this line, which was a little gentle in the beginning, would become more steep while the water is flowing through the clay layer. Okay, what would happen to this head loss while the water is moving again from the sand layer? Since the permeability of this layer is the same as the permeability of the initial layer, so the head loss in this zone would have the same slope as the initial one because the permeability of both the layers is the same. So this is going to be the profile of head loss over here. So how can we draw the equipotential lines in this case? Drawing equipotential lines in the first part would be the same as before. It is a sand layer, and in the sand layer, you will simply draw vertical lines like this, which would represent the equipotential lines. And this is something which is very similar to what you have done in the previous slide. But what would happen to the equipotential lines in this clear layer? Now, you know this thing from our discussion in the previous slides that the head loss between two equipotential lines is the same. So the head loss between any two equipotential lines is always the same. So in case of, so since this clay layer has low permeability, so there will be more head loss. And because in order to keep the principle of equipotential lines, the equipotential lines will become closer in this zone. What it means is that whatever was the head loss in this space, the same head loss was observed in a smaller space over here. So this is the property of equipotential lines. And then when we are in the second zone, the equipotential lines would again have the same spacing as the first soil layer because both of them have the same permeability. Let's see another example of drawing flow nets. Let's assume that we have a pipe, and inside this pipe, there is a certain soil which is filled in it. On top of this pipe, we have connected two piezometers as well. So we have two piezometers connected on top of the pipe, and there is soil filled inside the pipe. Now, if we inject water from one end, what will happen is that the water will start flowing, and once the water is flowing, because of the water head, water level will rise in the first piezometer, and when the water reaches the second one, water level will rise in the second piezometer as well. However, since the water would have lost some energy while moving from this first point to the second point, so because of this loss of energy, there would be some head loss, which would appear as a difference in head between the two piezometers. Now, drawing flow lines is going to be very simple, and it is simply going to follow the path of water particles, which will be straight in this case. So this will be the flow lines. How can we draw the equipotential lines? Again, it should be pretty simple. From your knowledge up till now, you know that this difference represents the head loss, and in order to draw the equipotential lines, you can represent the equipotential lines by straight vertical lines which are equally spaced, and this is something you'll call the equipotential line. And again, you should remember that on each equipotential line, the head anywhere on each equipotential line is the same. So head anywhere on this line is going to be the same, so as the head on any of the other lines is also going to be the same. Now let's look at some of the basic principles of drawing flow nets. So if you want to draw the flow nets, there are certain basic principles that you need to remember. The first principle is that the flow lines and equipotential lines are always at right angles to one another. So you look at this example that the flow lines and equipotential lines are making 90-degree angle with each other. Second principle is that the flow lines are always parallel to the no flow boundaries. Now, what do we mean by the no flow boundaries? It should be obvious that this edge, which is representing the pipe surface, this is a no flow boundary, or this is the impermeable boundary, because the water cannot flow across this surface. So because this is the no flow boundary or the impermeable boundary, so our flow lines are always going to be parallel to the no flow boundary, as you can observe from this figure as well. The third principle is that the equipotential lines are parallel to the permeable boundaries. So these equipotential lines are always parallel to the permeable boundaries. So the question is, what do we mean by the permeable boundaries? So this was the no flow boundary, so was this one. These were the no flow boundaries. So for a permeable boundary, you can see this end, and this end represents the permeable boundaries. So these permeable boundaries are the ones from where the water can either go inside or can move outside. So the point is that equipotential lines are always parallel to the permeable boundaries. So you can observe here that equipotential lines are parallel to the permeable boundaries. The next point is that discharge through each flow path is equal. So we have one flow path here, we have the second flow path here, and we have the third flow path here. So discharge through each flow path is always the same. So whatever is the water flowing in this flow path, same will be the water flowing in the second and the third flow path. The next point is that the head loss through each equipotential space is equal. So head loss through each equipotential space is going to be equal, means that whatever is the head loss in this zone, same would be the head loss in this equipotential space and the third and the fourth and all the equipotential spaces. So if you are to draw the flow nets of any flow of water through the soil, you need to remember these 5 principles. These are very simple principles, and if you remember those principles, drawing flow nets is going to be a piece of cake for you. So let's look at a few more examples and see how the flow nets can be drawn. Let's look at a slightly more complicated geometry. Let's assume that this time we have this kind of a pipe. So there is soil filled all inside this pipe, but this pipe is not straight, rather this pipe is curved. So how can we draw the flow nets through this pipe? Now, before drawing the flow nets through this pipe, just for your convenience, let me show you the 5 points that we have seen in the previous slide. So let's try to draw the flow nets of this pipe by following the same 5 principles that we have seen here. So what we'll do here is let's break down this complete pipe into 2 parts. We can, if we look closely, that we can have an imaginary line here, and on the left side, so this initial part is exactly the same as was in the previous slide. So if I ask you to draw the flow lines of this pipe, some partial flow lines of this pipe can be drawn like this. Why we can draw the flow lines in this part in a straight way? Because of the same principles that we have studied on the previous slide. So this first half of the pipe is exactly the same as the previous one. So the flow lines are going to be the same. And if you look closely, what we are having here is that these flow lines are parallel to the no flow boundaries or the impermeable boundaries. So how can we draw the equipotential lines in the same first half of this pipe? The equipotential lines again can be drawn in the same way as we have done before. Now the question is, how can we draw what will happen to the flow lines in the second half of this pipe? Now, following this principle, the flow lines are always going to try and follow the impermeable boundaries or the no flow boundaries. It means the flow lines will become curved when it moves to this curved zone. Okay, if we can draw the flow lines like this, how can we draw the equipotential lines then? Now, while drawing the equipotential lines, one principle is that they're always going to be parallel to the permeable boundaries. And another thing that you should remember is that flow lines and equipotential lines are always at right angle to one another. So we can see that there is a 90 degrees angle between the equipotential lines and the flow lines. How can we draw an equipotential line in this zone while maintaining a 90-degree angle with the flow line? Yes, you might have guessed it. This is how we can draw the equipotential lines while maintaining a 90-degree angle with the flow lines. So if you look closely, that this equipotential line has almost nearly a 90-degree angle with each flow line it is intersecting with. So is the case with the second flow line, third flow line, and so on. In the same way, it also satisfies this condition that equipotential lines are parallel to the permeable boundary. So one permeable boundary is over here because this is from where the water can go in, and the other permeable boundary is this end from where the water can go out of this pipe. So this equipotential line and the first equipotential line are again parallel to the permeable boundaries. So this is how we can draw flow nets in case of an axisymmetric condition. Let's look at another example. Now, this is the similar looking U-shaped pipe, but now the soil is filled in a slightly different way. So how can we draw the flow nets in this case? In order to draw the flow nets here, let's first see that this first part of the chamber is filled with water, so as the water is filled in the second part. And we also know from our prior knowledge that the head loss can be represented like this. So how can we draw the flow lines? The first principle is that in order to draw the flow lines are parallel to the impermeable boundaries or the no flow boundaries. So what are the impermeable boundaries here? The impermeable boundaries here are represented by the points A, B, and C, E, F, D. If you look closely, these lines represents the impermeable boundaries. So because they are the impermeable boundaries, so we can draw the first flow lines by following the path of these impermeable boundaries, as we have drawn here. Now, how can we draw the rest of the flow lines? The rest of the flow lines would be relatively simple. So we can simply fill in lines between the two extreme flow lines. We can fill in some lines between the two extreme flow lines which follow similar path, something like this. They represent the flow lines through this structure. Now, how can we determine the equipotential lines? Now, in order to draw the equipotential lines, first of all, we have to determine the permeable boundaries, because you know that equipotential lines are parallel to the permeable boundary. So first of all, we have this line CA as our first permeable boundary. In the same way, we have this second line BD as our second permeable boundary. And then what we can do is we can draw multiple equipotential lines in this zone while maintaining a 90-degree or a near 90-degree angle with the flow lines. So in the central part, drawing flow lines is very simple. We can easily maintain a 90-degree angle, but as we move close to the edges, the equipotential lines have to become curved to maintain a nearly 90-degree angle with the flow lines. Let's look at another example. Now, this is an example of a dam structure, you can say, where there is there is an obstruction to the flow of water. This is the soil. We have a soil layer over here, and we have installed a pile, a sheet pile, or a blockade to the flow of water. So if there was no blockade, this water here would have easily moved to the right side. But now, because of this blockade, the water is stored here. So it's more like a dam. So once we have water storage here and less water storage here, we have a soil here. How can we draw the flow nets in this case? Again, the first thing is we have to identify the no flow boundaries. Now, what are the no flow boundaries here? So we have water stored here. This stored water can follow the path of this no flow boundary, which is represented by this line BEC. So this is representing our first no flow boundary. In this, so once we have drawn our no flow boundary, in the same way, we can identify our permeable boundaries. Permeable boundaries mean the boundaries, because the permeable boundaries are important for drawing the equipotential lines. So how can we identify the permeable boundaries? The permeable boundaries are represented here by these red lines for your convenience. So we can call it as the upstream equipotential boundary and the downstream equipotential boundary. This is called as the upstream side, and this is called the downstream side. Why it is called the upstream and why is it called the downstream? Because the water is flowing from the upstream side always to the downstream side. So now we have drawn an equipotential line and a flow line. How can we draw the rest of the flow lines and the equipotential line? We know that the water is going to follow this path. This is our common sense telling us this is going to be the path of flow of water. So in the same way, we can draw some of our flow lines like this. And if we have drawn this flow line, we can draw a corresponding equipotential line. So you can see that this was our first equipotential line, and this flow line and also the second flow line, both are making a near 90-degree angle with them, both on the left side and also on the downstream side. Now, if I ask you to draw another equipotential line somewhere over here, how would you draw an equipotential line here? You might have guessed that this is how our equipotential line would look like. We can draw a similar equipotential line on the other side as well. So by doing so, we can extend the same philosophy further to draw our next flow line, and by following the same philosophy of maintaining a near 90-degree angle, we can draw our next equipotential line on both sides. And in the same way, we can keep on drawing our further equipotential lines, and this will complete our figure of flow nets. So this is how the flow nets around an obstruction would look like. Let's look at a similar example once again. So we have a tank which is filled with soil. There is an obstruction in the middle. There is water on the upstream side. There is little, so because of this water, the water has seeped through it and came on the downstream end. So how can we draw the flow lines and equipotential lines? The concept is again going to be similar. It's going to be exactly the same as you have done previously. So the flow lines, this is how the water will flow through the soil and appear on the downstream end. And once you've drawn one flow line, it should be relatively simple to draw the rest of the flow lines. And once you have drawn all the flow lines, you simply have to first locate the first equipotential line, which will be parallel to the permeable boundary, and the last equipotential line, which will be parallel to the last equipotential permeable boundary. And then simply by following geometry, you can draw the rest of the equipotential lines, which should be relatively simple. So this is a relatively simple experiment, which can be even replicated in the lab to see how the flow nets actually work. And this is what was done, what can be done in the laboratory as well. For example, whatever you have seen on the previous slide, this is a real life example of the same flow nets model. So this small sandbox model was prepared in my laboratory back in University of Tokyo, and I thought it was a very cool way of demonstrating this experiment to the students. So you can see we have just filled it with a box with sand, and we have just put some colors over here. And once we have put colors, then we start pouring water in it. And when we pour water in it, once the water flows through the soil, it takes the color along with it. And once the color moves along with it, it shows all these flow lines here. We tried replicating the same thing back in UET Lahore as well, and some of my undergrad students at UET Lahore, so they tried doing the same thing. So this is from their final year experiment that they did in UET Lahore. So you can see the flow lines, and what they did was they installed some piezometers here, one of which you might be able to see here in this image. So they installed some piezometers, they moved those piezometers at different locations. They moved those piezometers at different locations to draw the equipotential lines as well. So this is, once you are able to draw such flow nets, it becomes quite easy for you to comprehend and physically understand these things. So let's bring up a summary of all what we have studied so far, how to draw the flow nets. This is just a quick summary of what we have studied so far. So point number one, all the impervious boundaries represent the flow lines. All the permeable boundaries represents equipotential lines. The equipotential lines and the flow lines are always at right angles with each other. And the flow nets must be drawn in such a way that they should have some geometric proportions. So the shapes that are formed are somehow like squares or rectangles. And another very important point is, just like the contour lines that you draw in surveying, so the flow lines can never cross another flow line. So similarly, an equipotential line can never cross each other. And this is just a quick tip on how you can actually plot the flow lines. If we'll get some time, we'll see how to actually draw some flow lines, and this tip might be helpful over there. So let's see how the flow nets can be drawn for beneath a dam. So once we have a dam body, so because this dam is there to block the flow of water, so the water has to go beneath this dam body. So just imagine how the flow lines, how the flow nets beneath this dam body would look like. So I would suggest you to pause this video here and better draw this simple structure on your notebook first, draw the flow nets before proceeding further and seeing how the actual flow nets look like. This is how the actual flow nets would look like. So the flow lines representing the flow path of water, and then equipotential lines which are representing the head loss across this. And as we have discussed multiple times previously, that the main characteristic of these equipotential lines is that anywhere on an equipotential line, the head would be the same. So whatever would be the head over here, same would be the head over here or anywhere on this line. In the same way, we can think of another example of another dam structure. Now, there is a slight difference in this dam structure, and the difference is that at the downstream end of the dam, there is a toe filter here. Now, what is a toe filter? In case of dam structures, the water enters the foundation soil from the upstream end, and then it moves beneath the dam body and then comes out from the downstream end. When a lot of water is coming out from the downstream end, so once this water is coming out of the soil, so it is the pressure is so high many times that because of this pressure, the soil at this downstream end, it starts eroding. So in order to release this high pressure, it is often done that the downstream end of the dam structure, a high permeability material like gravel is provided near the toe of the dam. Now, what is the objective of this toe filter is, now this toe filter comprises of a high permeability material. If this comprises of a high permeability material, so once the water is flowing from over here, so instead of water following this path and exiting from here, the water always try to exit from this point, because this part has high permeability, and because it has high permeability, because of high permeability, it is easy for the water to flow through this. So all the water which is flowing from the upstream end to the downstream end, it terminates over here at the toe filter. Now you can understand the basic phenomena behind the toe filter, I would again request you to pause this video here and try to draw the flow nets for this structure. So now you can just compare your answer, the flow nets that you have drawn, with this one. So you can see the flow nets, all the flow lines which are terminating at the toe filter, because this has high permeability, and because of high permeability, it is very easy for the water to flow through this. And the equipotential lines are once again drawn by maintaining the basic geometry that such that the angle between the flow lines and the equipotential lines remain almost 90 degrees. Let's look at one more example of us again of a dam structure. Now in this dam structure, we have provided a sheet pile beneath the dam body near the upstream end. Now if there is a sheet pile here, which of course blocks the flow of water, so how will the flow nets look like? Again, you have to pause the video here, draw the flow nets on your notebook first, and then see the result and compare your answer with it. So this is how the final flow nets would look like. So the water entering from the upstream end, going all the way through beyond the sheet pile and exiting at the downstream end. And correspondingly, I hope now you would be able to draw the equipotential lines by yourself. So in these three examples, we have seen how the water flows beneath the dam body. So the water flowing below the dam body, we have seen in the last 2-3 examples. But it is not always the case. There are many cases in which uh, in fact, in almost all the cases, the water that is blocked on the upstream end not only moves beneath the foundation, but it moves beneath the foundation and also through the dam body. So because this water is so much, the pressure of the water is so much, and the soil that we use to block the flow of water, it of course has some permeability, although we try to make it as impermeable as possible, but still it always has some permeability. So because of this permeability, there's always some flow of water through this. And this is how the flow nets look like. Flow nets of water flow through the dam body look like. So water from the upstream end, it moves through the dam body and exits somewhere near the downstream end. This line represents the phreatic surface, which represents the top surface of the water level. And again, you can see that since a lot of water would be flowing through the dam body, and this water would be exiting from here, once this water would be exiting from here, it would be exiting under huge pressure. And this pressure can erode the dam body from here. And if it starts eroding the dam body from here, you might end up with a case something similar to the tendon dam example that we have seen in the previous lecture. So what we often do is we provide a high drainage material near the toe. The benefit again of providing a high drainage material is that instead of this water going through the toe, all this water is accumulated near the blanket drainage and is easily drained off. Because this material has very high permeability, so it is very easy for this material to drain off any water that is accumulated within the dam body. And then finally, just to give you a quick overview and to tell you something about the practical civil engineering related to seepage flow, there's a very useful software which is called SeepW, which comes with the GeoStudio software package. And all the flow nets that we have been seeing in the previous slide, these flow nets can be drawn very easily by using the software. Now, this image represents the flow nets which have been drawn using SeepW software. So you can draw flow nets quite easily by using SeepW. If we'll have time, sometime later, I might give you guys some tutorial of how to use SeepW for drawing flow nets, but that you cannot do until and unless you have very good concepts of seepage and permeability through the soil. So I would suggest you guys to improve your knowledge about seepage and permeability, and then if we'll find some time later on near the closure of the semester, we might add a couple of lectures for how to use SeepW. Anyways, so this is pretty much it for the day. And before we leave, I have added a couple of sample flow nets for you guys to see by yourself. So these are a few sample flow nets for you guys. What I want you guys is to have a look at these flow nets by yourself, try to understand these flow nets by yourselves, and then whatever questions that you have, we can have those discussions during our online discussion session uh, in the next class. So that's it for the day. Thank you very much.